Howdy. In this lesson, we're going to be applying our previous two lessons to the idea of finite wings, and we're going to be arriving at something called lifting line theory. So remember that we were modeling our finite wing as a vortex filament that traveled along our span and then turned at our wingtips to go towards positive infinity in the x direction. Now, we can apply the Biot-Savart Law to actually calculate the downwash at a given point. And this is going to be due to the gamma, so this gamma is constant, over 4 pi times the integral from 0 to infinity of dl cross r divided by r cubed. And remember that we rewrote this as gamma over 4 pi h times the integral of negative sine theta d theta. But before we integrated from negative infinity to infinity, and now we're just going from 0 to infinity. So infinity is going to stay the same. Infinity stays at theta equals 0. But 0 is going to be theta equal to pi over 2. So what we have now will be gamma over 4 pi h times the integral of sine theta, which is negative sine theta integrates to cosine theta. We're going to evaluate that at 0 and pi over 2. So cosine of 0 minus cosine of pi over 2. This is going to be 1, and this is going to be 0, which means that this entire thing evaluates to 1, which means that our upwash due to this vortex filament is simply going to be gamma over 4 pi h, where h is just the distance from our filament to our downwash location. So this is great, but now we're interested in actually finding the lift over our entire wing, right? So we say that rho times v infinity times gamma is equal to our lift per unit span, and we're saying that this is a function of y. And we can rewrite this as q infinity times s times the coefficient of lift. And we can rewrite that again as 1/2 rho v infinity squared. Since we're doing lift per unit span, s just becomes a c, and then cl is going to be 2 pi alpha. But remember that alpha, that this sees, that our airfoil sees, is going to be changing due to our downwash. So we have to write alpha effective. All right, let's simplify this out a bit. We're just going to take gamma is equal to all this nonsense divided by rho v infinity. So let's simplify. 1/2 cancels with the 2, and so we end up with c times v infinity times our pi times alpha effective. And we can write alpha effective as alpha minus alpha induced. And this induced, alpha induced, is where our downwash comes in. So our alpha induced is going to be a negative downwash as a function of y divided by v infinity. Now, there's a problem with this, because our downwash at the wingtip, if we evaluate it right here at the end, well, this approaches infinity. And in order for this gamma to stay constant, then our alpha, our geometric angle of attack, is going to have to try to counteract that. So this is going to have to be equal to infinity. Well, that doesn't make sense. So we're going to have to change our model a bit. And the way that we're going to change it is by saying that this gamma, this vortex filament, is going to change strengths. And what do I mean by that? We're going to have a vortex distribution, a lift distribution over our airfoil. And we're going to say that gamma is going to be a function of y. But, you say to me, what about Helmholtz? Well, Helmholtz says that gamma is a constant. So if I'm changing the gamma up here, I need to have more vortex filaments. So instead of a single vortex filament, we're going to have an infinite array of these trailing off behind. So in order to change the gamma, we're going to have to create an infinitely large number of trailing vortices, which all have slightly different strengths. And what are those strengths going to be? Well, we're going to call them d gamma. So each of these trailing edge vortices is going to be a d gamma, and it simply specifies how the vortex distribution will change as a function of y. So we can write this as d gamma by dy times dy. And why do we want to do that? Well, once we get to that point, we can say that we're looking at our span, and we're saying that we're going to have some vorticity, which is going to be defined by these d gammas. And more specifically, that is going to be d gamma by dy times dy. And we'll be looking at the effect of each of these infinitesimal gammas, each of these trailing edge vortices, on the downwash at another location. And we're going to have to do a similar trick as before. We're going to call this a y naught because we're going to have to integrate all of these vortices, all these infinitesimal vortices, along our y direction. But we're only interested in a constant y naught for each of these w's, for these downwashes. So our downwash is going to be equal to the integral over our entire span, and our span goes from negative b over 2 to b over 2. Our vortex strength in this case is going to be d gamma by dy, and we divide that by 4 pi, keeping with our Biot-Savart Law, and then we need this distance, and this distance is going to be y minus y naught. And if y is less than y naught, then we get a negative w, which is what we expect. And then we're integrating along dy. So this downwash is the result of taking a constant gamma, a constant lift, and changing it so that this lift is modified across the span. And the end result is a formula that looks somewhat familiar to, or somewhat similar to, the formula that we used for the camber line. But now we are integrating the trailing edge, or the wingtip vortices, the trailing vortices that are coming off of this bound vortex. And we're integrating the effect of all of these on the downwash at a given point.